In this screencast, let's explore how the number of floating point operations scales with the size of the matrix. In a previous screencast, we saw that decomposing a 2 by 2 matrix required 3 floating point operations. Decomposing a 3 by 3 required 13. How about a 4 by 4? If going from a 2 by 2 to a 3 by 3 increases it by a large factor, 4 by 4 ought to get bigger. How about 100 by 100? Or even 1,000 by 1,000 or 10,000 by 10,000? As it turns out, there's a dramatic increase in the computational power needed to decompose these larger matrices, and in fact it scales with n to the third power. To explore that a little bit more, this is a bit of MATLAB code written to decompose this 2 by 2 matrix. In the algorithm there's 3 loops, an outer loop, a middle loop, and an inner loop, and the outer loop will start out with k equal to 1, and we'll run it from 1 to n minus 1. So in this case n is equal to 2. We'll only run through the outer loop once. The middle loop will run from k plus 1, so we'll start out with 2 and end at 2. So again, for this 2 by 2 matrix, we'll only run through the middle loop once. And then the inner loop will run from k plus 1, which is 2, up to n, which is also 2. So we'll only run through this inner loop once. Computing each of the factors only requires one floating point operation, one division. But scaling each row requires 2 floating point operations. We've got a subtraction and a multiplication. So if I run through this code, I'll start out with the number of floating point operations equal to 0, add 1 for each pass through the middle loop, and add 2 for each pass through the inner loop. And then finally, let's output the number of floating point operations that were completed. And what we'll find, just like we did with by hand, if n is equal to 2, flops is equal to 3. Here's the same algorithm used to decompose a 3 by 3 matrix. The outer loop will run from 1 to n minus 1, so 1 to 2, so we'll run through this loop 2 times. The middle loop will run from k plus 1, or 2, to 3, so we'll run through this one also 2 times. And the middle loop, similarly, the middle loop will run through this 2 times. So let's try to figure out how many floating point operations is required for n equals 3. And to do that, to cycle through these 3 different loops, I've made a table, and I'll call it k, I, and j to keep track of the 3 indices. And then the number of flops, this will just be a running total of the number of flops as those 3 indices change. So we'll start out with no floating point operations before k, I, and j are even defined. As we move into the outer loop, k is set equal to 1, and then I is set equal to k plus 1, so I is equal to 2. And we move through this loop, and we incur 1 floating point operation at that location. And then we move into the inner loop, defining j as k plus 1, or j is equal to 2. At that point, we incur 2 floating point operations. And then we'll loop through it again when j is equal to 3. The number of floating point operations has been increased to 5. And then because j is equal to 3 and n is equal to 3, we move out of the inner loop back into the middle loop where I is incremented from k2 to 3. In this case, we incur 1 more floating point operation. We'll move through that inner loop 2 more times with j is equal to 2 and 3, so we've incurred 2 more, so it goes from 6 to 8 up to 10. And back in the outer loop, k now becomes 2. Move into the middle loop, I becomes k plus 1, or 3. And then we incur 1 floating point operation, so we've got an 11 total, and then we move into the inner loop with j starting out with 3. We only move through that loop once, and we come up with the final number of floating point operations equal to 13, which is what we saw in the previous screencast for n is equal to 3. Let's look for a more general case in which we can set n to anything we want. Here I've written some code in which a random n by n matrix, set n is equal to 100, will generate a matrix A. We'll run the algorithm on it and keep track of the number of floating point operations. A more sophisticated analysis of these looping structures will show that the number of floating point operations will be about equal to 2/3 times the size of the matrix to the third power. And that's true for a very large n, and as we'll see here in a second, that becomes a really nice approximation when n is large. So I ran this code with n equal to 2, n equal to 3. I ran it again with n equals 10 and n equals to 100. And I prepared this table where I charted the number, or n, and then the value 2/3 n to the third power, and then the actual number of flops, and then a ratio between this scaled power and the actual number of floating point operations. So there's n equals 2. The actual number of floating point operations is 3. At 3, the actual number is 13. The ratio gets a little bit better. Remember, we want a ratio of about 1. If n goes to 10, we're predicting 667 floating point operations, but in reality we only needed 615. But that ratio is becoming much closer to 1. And indeed, if I increase n to 100, we have close to over 660,000 floating point operations. The 2/3 to the n cubed power predicts something closer to 670,000. And this ratio becomes very close to 1. And the limit, if I ran n equals to 1,000, for example, we'll get a ratio that's even closer to 1. And when I run a 1,000 by 1,000 matrix, I calculate it required over 666 million floating point operations, and that agrees really well now to that 2/3 n to the cube power, and that ratio is again very, very close to 1. The reason counting the number of floating point operations is so important or so significant is that the computational time scales with the number of floating point operations. So on average, each floating point operation requires a certain amount of time. And here I've run simulations ranging from n is equal to 1 to 200, and I recorded the number of floating point operations required to do each one, and then I recorded the amount of time it took to process each one of those. And what we see is a very nice linear trend. The processing time is proportional to the number of floating point operations. So here on the right, there's a factor of 1,000,000, so I'm running a number of floating point operations from 0 to 1,000,000. And then what I looked at was the number of floating point operations required as a function of n, with n ranging from 0 to 200. And I've actually got two lines here, and they follow right on top of each other. But the first one is the actual results, and the other one is this 2/3 n to the cube. So the number of flops, it's approximately 2/3 n to the third power. It's hard to distinguish it, but if I zoom in on it, maybe we could distinguish it a little bit. But one of the curves is the actual number of floating point operations, and the other curve is that 2/3 n to the third power. So finally, what might be most interesting is the processing time required to process n ranging from 0 to 200. And again, there's this dramatic increase, this n to the 1/3 power. So we see a huge increase in the processing time as n gets larger and larger. And just to clarify, let's say, for example, we had n is equal to 100, so 2/3 times 100 to the third power. And let's see how much longer that would have taken if we compare that to n is equal to 10. What that says is going from a 10 by 10 matrix to a 100 by 100 matrix would require 1,000 times longer to process that larger matrix. So big consequences here with that n to the third power.